So this is joint work with Kieran Vojrahali at Columbia University and Christy Vasile and Daniela Rus at MIT. So imagine that you're an alien and you've visited Earth and you need to learn how to drive. So you have to learn not just how you can drive a car, but also the rules of the road. So ways that you could learn the rules of the road is by watching other cars drive. So you would learn that people stop at red lights, prefer the right lane, and that they don't run into other cars. So these would be the rules of the road, and once you have learned these rules, you would hopefully be able to get into a car and drive on the street safely. So a crucial element of your learning is that you would conceptualize the rules separately from the low-level actions, and you would have a representation of the policy in your head that is interpretable. So we also want to learn interpretable policies, and when I say interpretable, I mean that the structure of the learned policy is grounded directly in meaningful interpretations. So next, you also might, let's say that you observe like a bad driver, maybe even a bad self-driving car run a red light. So you might think to yourself, since you're an alien, oh, like humans run red lights 1% of the time, so I should too. So a police officer should be able to tell you, no, never run a red light. And this should be possible because the representation of the rules in your head is manipulable and can therefore be made safe if you learn from a faulty expert. So by manipulable, I mean that a human operator can easily modify the learned policy to perform similar but different policies. And manipulable does not mean composable. Compositionality is when you can compose different policies together to form a new policy. But by manipulable, I mean that it's actually simple to modify your learned policy to change the behavior of the agent. So to restate, our goal is to learn from demonstrations not just a low-level policy, but also a high-level policy that is interpretable and manipulable. And from these two properties, we can learn not just from learn from demonstrations, but also modify our learned policy to be safe. So this, since rules govern many parts of human life, I think that this is useful beyond just an alien learning how to drive a car. So in the case study of driving, here's our simplified driving environment. So this car is following certain rules like avoid obstacles and work zones, prefer the right lane, do not run red lights, and eventually reach the goal. So how can we learn these rules from demonstrations such as this one? So we make a few assumptions. One assumption that we make is that the rules can be encoded as a finite state automaton. We assume that relevant features of the environment can be detected, that the number of FSA states is known, and that the environment outputs the current FSA state as well as the low-level state at each time step. And from this, we want to learn the transitions between FSA states as well as the low-level transitions. So when I say that we can detect relevant features of the environment, I mean that these features can be treated as logical propositions, where a proposition is like a true-false variable. So in the driving domain, propositions would be like the black blocks are obstacles, and those could be labeled with the variable O. And it's true when there is a block, and it's false when there is no block. And the same goes for like green lights or red lights. So the red light is like the letter R or the variable R, and that's true when there's a red light, and it's false when there's no red light. So we assume that the expert is following some sort of controller, like a finite state machine controller, such as this one here. So here it's like this is the initial state, this is a state at a red light, this is the reached goal state, this is a state that's unused in practice, which is it's at the red light and the goal. And then you have like a right lane state and a left lane state. So this is a single FSA that we just split into two to make it easier to understand what's going on. But we assume that the expert is following this FSA, and we kind of want to learn, this is what we want to learn. So how does this work? Our model is based off of, so we kind of base this off of value iteration networks. So the value iteration network architecture is like a fully differentiable version of value iteration, where you calculate the Q function using a convolution and the value function using a max pool operation. And this lets you learn the reward function and the transition function. One limitation I should note about these value iteration networks is that they work best on like a grid-like environment, like a 2D grid-like environment, because of the structure of a convolution. So this is our architecture. We call it logic-based value iteration networks, or LVIN. So it's kind of like you have, so there's two ways that this differs from the normal value iteration network. One is that we essentially have like a value iteration network for every logic or FSA state. So this lets us learn the reward function and transition function for each FSA state separately. And then in addition to that, we also apply a second convolution afterwards. And this convolution is based off of the transitions of the FSA, and this lets us learn the transitions of the FSA in the same way that the transitions of the low-level environment are learned. And there's more details to this, and if you're interested, please come talk to me. So what makes LVIN different from like other hierarchical models? One is that we interpret the high level of the hierarchical model as an FSA or as a logical specification. So we hope that this makes it more interpretable than other ways. And we incorporate the FSA directly into the value iteration so that the changes to the FSA result in changes to the policy, which makes it manipulable. So we tested our model on a few different domains. One domain is the kitchen domain. It's a strange kitchen, but what you want to do is, what the expert does is it first fetches milk, and then it fetches cereal. So the idea is that the expert teaches our model to first get milk, which allows it to transition to state 1, and then pour cereal into the milk, which allows it to transition to the goal state. But let's say that you don't like it when your cereal is floating on top of your milk, and you want it so that you pour the cereal in first and then the milk. So instead of retraining from scratch and needing new expert demonstrations, since we have this representation as an FSA, you can just switch the two transitions so that cereal causes your transition to state 1 and milk causes your transition to the goal state. So we tested this out. We learned from expert demonstrations, and then we modified the policy, and it gets like the same very high performance on the manipulated policy without any additional training. So another example is in the driving domain. Let's say that you've been observing a lot of bad drivers, and you have this. Here's just a fragment of the learned FSA, where you've learned that you ignore the red light 10% of the time, and you stop at the red light 90% of the time. So once again, since the FSA is interpretable and manipulable, all you have to do to fix this is just change the transition probability so that you never run the red light. So yeah, we tested this, and as you would expect, for the unsafe FSA, it runs 10% of the red lights, and the safe one does not run any red lights. So for next steps, if you recall, we made a few assumptions, including that the rules are encoded as a FSA and that we assume that relevant features of the environment can be detected. But we'd like to get rid of the assumptions that we know the number of FSA states and that the environment outputs the current FSA state at every time step. So I think that this is possible, so that's what we're working on right now. So that way, the goal would be to infer the number of FSA states as well as the transitions between them. So yeah, thanks for your time. If you have any questions, please let me know.
We have time for a few questions.
Thank you for a great talk. So once you learn the high-level logics, can you compose different logics? I mean, you learn some high-level stuff from one task and then another task, and then given these tasks and then high-level structures for these, can you, compose these to create a new kind of high-level?
I actually haven't thought about that. One limitation of the manipulations is that you can't add. Is that at least the way we have it now, it's very difficult to add new states and new propositions. But I think it's probably possible with like some. Yeah,
I think if you can do that, maybe you can, think of a transfer learning. Because you can, given new tasks, maybe you can think of how we can compose, the given high-level structures or something like that.
Yeah, I think it should be possible, but not with the way it's currently modeled. Yeah. Sorry.
That's fine.
So one question I had is, so with the cereal and milk example, you learned to do cereal without milk, and milk without cereal, right? And in your particular example, that was okay. But what if it turns out that if I if I do it in the other order, I actually have to do the second step in a different way because a different state variable is on. Right? So there's a kind of compositionality that you're relying on that might not always be there. Is that right?
Yeah, I think that is like a problem right now. Yeah, but I think it's like our current architecture is like very limited, but I think it should be possible to like fix that eventually.
Okay, last question.
So what sort of manipulations are allowed under the assumptions that you have? Do you are you only changing the state existence and transition probabilities, or
Yeah, so
what
like
other things?
the way it is right now, you can't change the number of states or the current propositions, so you can only change like how you control the transitions between states. Yeah. So you could control like which propositions trigger transitions between states. Yeah.
Let's
Thanks.
thank Brandon again.